Hi everyone. So the idea behind this presentation is to give you a brief introduction on our paper, which was created during my master thesis when I was in the Technical University of Delft, together with my tutors Michela and Martin. We started this research by asking the question, what about speech and noise perception in an indoor environment, and mostly when we have a multi-talker scenario. Usually these projects come with a tight budget on the acoustics, and this creates a problem on intelligibility. So the objective was to create something for designers aiding their decision-making process when they do iterative exploration of ideas, giving them visual feedback on numerical outputs for speech intelligibility. We had in mind something like that, a space that is not designed for acoustics, but it spontaneously can host social gatherings, and people need to communicate and collaborate under noise. We didn't have in mind the imminent future of the pandemic, so social gatherings at this point seem very different, and the acoustic challenges also are completely different. But hopefully this is something for the short term, and we will quickly resume and go back to those scenarios where noise is a problem. And the problem lies that noise and speech are transmitted in a single stream, so it's difficult to recognize the message from the DIN. And usually the receiver is exposed to informational masking, confusing the source. So how can we actually go a step closer to the acoustics of, let's say, a music hall without the computationally acoustic analysis that this requires in order to be perfectly tuned? We created a workflow that could help designers with this process. And we have to highlight that this workflow isn't about deliberating on the level of the accuracy of the results, but it is to give a visual feedback on the acoustic performance for iterative design explorations. So we define the scope. We moved from absorption to diffusion and from macro geometry to microgeometry. We focus on periodicity, and this was the way that we classified the different patterns. And we defined a global set of properties in order to compare the different patterns that were generated. For the selection, we lastly introduced the correlation scattering coefficient metric. And all in all, the idea was to create a speech intelligibility assessment. Moving from absorption to diffusion, we thought that this step is important. Mostly if we go into research, we see that outdoors versus indoors, usually the acoustic environment is more sound in an outdoor setting. And this is because in an indoor environment, there is high reverberance for low frequencies. And these low frequencies is actually the vowels. So vowels are the ones that are responsible for speech power, and those are amplified indoors, masking the consonants. And it's important to mention that actually consonants are the ones responsible for speech intelligibility. So the idea that started all this was to absorb low frequency vowels, whereas diffuse high frequency consonants. Most of the research is done throughout the years about absorbers. There are various devices that can control background noise levels and improve intelligibility. Only the recent decades, research towards diffusers is introduced, and actually, in most of the cases, this comes with extensive research because they come with problems as far as uniform dispersion of sound is concerned. The idea is to try and use modulation schemes and sequences in order to eliminate periodicity and don't have repeatability in the patterns. Eventually, the current state of the art is towards a hybrid approach where diffusers and observers are merged. Moving from macro scale to micro scale, it is important before we start comparing patterns to set the amount of absorption and diffusion that it's needed, and then the relevant frequency range. For this task, we thought to define the user group and the task. In our case, it was preschool children and play, so interactions. And then speech intelligibility is about room geometry, signal to noise ratio, background noise levels, and reverberation time. So based on those, we ended up with a medium to high percentage for diffusion in high frequencies. And this is where the study goes further. Picking the patterns, we decided to classify patterns based on periodicity because this is something that makes a big difference when we talk about sound energy dispersion. So a pattern can be periodic, non-periodic, aperiodic, or partly periodic. And in order to compare those, we introduced the correlation scattering coefficient metric. And until now, mostly when we measure scattering performance, we check it with the isoscattering coefficient, which gives the amount of energy reflected in the specular direction. What we propose is to check the dissimilarity between the test and flat surface. This is a procedure done by a plugin for Grasshopper, and it actually gives a quick result on this. The main difference is that the standard method uses random incidence, whereas this method uses normal incidence. Though periodicity is highly dependent on the incidence angle, the perfect, let's say, diffuser would be something that gives a constant polar response independently of incidence angle or frequency. So this is where we want to get. But both methods actually do not give an indication on the quality of the produced dispersion, whether it's uniform, but they do give an indication of how much energy is reflected from the specular direction, and this is a good first step. We decided to define a global set of properties for our comparison purposes, and the three important points for us were scale, profile, and well depth. For this, we created 20 different iterations, selecting three representative tiling arrangements. So an aperiodic, a non-periodic, and a partly periodic one. We started by giving 2 depths and varying the variables, and we plotted the results. So to interpret the results, we created a bounding box. This was based on the relevant frequency range that we described earlier, and the amount of diffusion that we wanted to target, so medium to high diffusion for these frequencies. And eventually we ended up with a plot that is fully enclosed in this box only for the aperiodic pattern. This is not to say that aperiodic patterns are performing better, but in the context of this study and under the samples that we tested, this was kind of the result. And it shows actually the potential of periodic order for uniformly distribute the flow of sound energy. Just to check on increasing the complexity level in order to relate it to periodicity, we decided to use various depths. So we wanted to check whether these samples gave better results, and eventually we ended up with worse results, meaning that increasing the complexity of the pattern doesn't really necessarily mean that you get a better scattering coefficient performance. After this, we ended up with an optimized set of variables, and these we grouped them depending on the periodicity. So for designers to have a rule of thumb in their selection of variables. And just for a quick play, we couldn't have a designer that tries to compare different patterns. The way he would work, she would work, would be to select a pattern based on periodicity, go to the rule of thumb matrix, select the right variables, big scale, for example, if it's an aperiodic pattern, and 2 depths because it's no need for various, and then he sees the plot. It's not fully enclosed in the bounding box, but if he goes for the 50% well to width ratio as the matrix suggests, then he gets a better graph. And he could also further implement absorption and turn it into a hybrid device. And he could eventually end up with a pattern, with a structure that modifies spatial, but also the acoustic performance. So if you manage to reach this point, it means that you're a good listener. And we thank you for that, and see you online.